Okay, thanks everybody for coming early to the early defense here for Lirui. So, okay, let me just say a few words. So first of all, you see in the title, Lirui is going to tell us today about fleet learning, which I think is just a super important topic, right? So I think I've been working on robot learning in various capacities for a long time, but always in optimization, but always thinking about how do you learn the first skill, right? And I think that's just kind of wrong in the new age of learning. What's going to happen is we're going to have massive models, lots of robots on the edge, and when one robot learns, they all learn. And that, if you change your perspective to that, I think it kind of completely changes the questions the way we've been asking them. And Lirui's really been the first in our group to start diving headfirst into that problem, trying to build some of the intellectual framework around it. Another thing that's kind of I've been reflecting about is that I think the world of robotics is changing into this, it's going through this evolution into sort of big science, right? Where it takes teams of people and big data sets and lots of compute to do some of these ideas, not all of them. But Lirui never got the memo on that. He just does it all himself. So he has done more extensive compute than many large teams. He has collected bigger data sets, run more jobs, run more analysis than anything. I think that will come across in his presentation today. The scale of his execution is truly astounding, absolutely astounding. And the other thing maybe I'll say is that the shift that we're seeing even in the robot locomotion group has been, we have some people that are trying to really push on the fringes of learning and some people that are still trying to think really carefully about models, and the group is sort of bringing these together. But Lirui and Boyan maybe are kind of our most learning people, and they put up with a lot of conversations about convex optimization and physics and stuff like that. I suspect that if you never hear another convex relaxation story in your life, you'd be okay. But I do think he's brought a very important sort of voice into the lab over these years, keeping us plugged in, up to date. It's been very interesting to seeing how he communicates what's happening in the field to the group and vice versa. And that's been very, very healthy. So it's been great. And I'm looking forward to your talk today. So thank you.
Okay. Thanks, Russ, for the introduction. Okay, now let's get started, maybe. So today I'll be presenting my thesis talk on robot free learning from heterogeneous data. If we look at the history of robot learning, there are two predominant paradigms. One is reinforcement learning, and the other one is imitation learning. So for reinforcement learning, for the past 20 years, significant progress has been made from locomotion to manipulation. Today's talk is more going to be focused on imitation learning, which has its application in self-driving cars back in 1988. So both of these paradigms can solve any single task really well, but what can imitation learning do today? Well, today, manipulation demos from imitation learning work surprisingly well. We see that humanoids can help with assembly in the factory. Robots can help with the kitchen tasks in the home. However, these demos are often brittle, even with hundreds of examples. They often work for a specific environment, for a specific task, and for specific robots. For instance, if we took the figure setup and we moved the table by 10 centimeters, the same policies might not work. So the question today is, how can we get more generalizable robots? Many people believe that scaling up foundation model can be a solution. For example, LLM show very impressive capabilities by training with code data, translation, and you can do multiple tasks together. And even the state-of-the-art Llama 3 model is shown to train on this kind of mixture. And these days, multimodal foundation models also add image input, video inputs, audio inputs, but their heterogeneity is still quite low compared to robotics. So a natural question to ask in robotics is, why don't we just scale up and pull all the data together? And again, different from other fields, there's huge data heterogeneity in robotics. So what specifically do I mean by that? Well, first, we have different kinds of hardware configurations. In addition to different cameras, for robotics, we have different proprioception and action space. So just to be very clear, proprioception means the sense of body movement, position, and force, right? If I can close my eyes and take the phone out of my pocket, that's leveraging proprioception. So for instance, the 7-DoF robotic arm here is very different from a 23-DoF humanoid. And if you're also considering actions, these robots can be operating in different frequencies. So you can have robots operating 2 Hertz, or robots operating 50 Hertz. And even for the same embodiment, if we are changing any factor in the lab, we don't want to recollect the data and retrain the policy every time. And what's the second kind of heterogeneity? It would be sensor modalities. So robot needs to learn from different kind of modalities, just like human. You can learn from point clouds, you can learn from color images, language instructions, proprioception, and tactile images. This is very different from just pure language modality. And finally, we have different kinds of data domains, right? This can include human videos, simulation, teleoperation, and deploy robots. Each of these domain has its pro and con. For instance, the human videos, we have a large amount of them on the internet, but it has the embodiment gap. The simulation, we can generate infinite number of them, but they have the sim to real gap. Teleoperation is good, but it's kind of expensive. It's good. So if we compare the language domain to robotics, again, it's very homogeneous. They're all in the text form, right? If you think of the real world as a big box, the language data, which is like to train a GPT-4, is already on the internet. So it covers this box really well. So we just need to have a centralized data and train it in a top-down fashion. However, in the robotic case, we don't have so much aggregate embodied data on the internet. We have inside this big real-world box, we have smaller islands of data that are scattered around. And these robots, these robotic data, they are very heterogeneous. And now we still need to train on them bottom up to generalize to the real world. You probably have heard a lot of complaints on we don't have so much data for scaling, but is this really the case, or are we just bottlenecked by the current methods? If we follow the standard procedure of unifying all data and training on them together, we will see that we don't have so much data. For instance, proprioception that I just talked about is very important, but it's often very heterogeneous. It's not very easy to unify them in the same format, and therefore we will lose this part of data. Also, there are companies that are generating huge fleet of data. And if we don't know how to leverage this data efficiently, or if the companies don't have the motivation to share this data, then we will also lose this part of the data. And finally, sometimes we want to reuse the data, right? For instance, I have to recollect data for every single project that I did here. What if we have a method that can reuse the trend policies? So my work is going to tackle all these 3 problems and try to bring the data back. Therefore, to me, the most important and challenging question right now is how do we train a generalist model under such data heterogeneity? And the answer is going to be fleet learning. So now I'm going to introduce the goal of my research, which is a general concept called robot fleet learning. The objective is a minimization of parameter theta over a combination of k datasets. As general as it seems, the loss function can be self-supervised learning loss, behavioral cloning loss, and the parameter can be transformer, CNN, etc. The important thing is that the datasets are heterogeneous. And why is this the case? If we imagine that we want robots, a lot of robots to operate in a house, they would naturally be generating their own data and they're doing their very specific task. And we as robot learning researchers, we want to develop a method that can aggregate this data to learn a generalist model and then specialize it again for each of the applications. So here's the outline for today's talk on fleet learning. If you look at this chart of heterogeneous learning, well, in the very left, where I didn't show is LLM, where we have just full homogeneity. And we're going to first add heterogeneity to the setting to say that, okay, how are we going to pre-train with heterogeneous data? And then we'll go one step further. We will say the data are actually not allowed to be pulled together. They're decentralized, and they could even be unlabeled. Now, can we figure out a way to align the representation? And then we push this idea to control to see if we can apply the idea of model merging for policies. And finally, we say that, okay, the policies are now all trained, they are fixed. Now at test time, can we have a method that can compose these learned skills? So let's get started. First, we will look at data and ask the question, how do we pre-train on heterogeneous robotic data? So one way to think about this is that the standard pre-training for representation learning would either assume no heterogeneity, or you will handle it with a very expensive pre-processing step. In this new project, we're thinking of heterogeneous pre-training, where we have a separation of network module, and we're going to update a shared representation in this pipeline. So if you think about training a single generalist policy that can control all these kind of robots, it's not very easy, right? We really want to learn a shared latent space that can be applied to these different robots. For instance, we can have a Franca robots that's doing some kitchen tasks. We can have UR5 robots, and we can have another robot that's doing planner pushing. These robots are all very different. So a naive way of unifying all of these different data is to pad them, right? Just like padding sentences in LLMs. So what if we have two post representation? The first one's X, Y, Z and raw pitch yaw. The other one is post representation, but with quaternions. Can we really pad it with 0? It doesn't seem very natural to me. Now, what if we have another 7th representation, which is joint angles? Now we don't need to pad, but can we really train them together? So I'm going to introduce a new pre-training method that's able to handle this problem, and it's very simple. And the idea is called heterogeneous pre-trained transformer, or HPT. HPT modularizes the network architecture through stem, trunk, and head. So we're going to focus on single domain. So we have stem, the trunk transformer, and the head. So the key difference of HPT is that we will put the proprioception before the transformer. We will process it with stem. And this allows us to align more modality and also process this important proprioception information with a very computation-heavy transformer. And for many years, the standard practice is to add proprioception only to the head. And this is done differently in our case. So what's stem? To give a bit more details, the stem network is effectively just a cross-attention. It tokenizes different modalities into tokens by using learnable query tokens of the neural network's parameters. So in this case, it can be 8 learnable tokens, which are cross-attended with the vision and proprioception features of the observation. So now the question is, what if we have multiple embodiments and we want to train on them, right? We train with heterogeneous embodiment, what do we do? So intuitively, we will have some parts in the network that are handling different embodiments and some parts so which cannot be shared and some parts that can be shared. So for instance, the transformer here will be shared and it will learn a representation. So this is, for instance, so like the stem and the head pair in this case will be activated based on the embodiment. In this case, head 1 and stem 1 will be activated. In this case, head 2 and stem 2 will be activated. So the training objective is chosen to be supervised learning with smooth L1 loss across all the data sets. So compared to earlier works such as Octo and R3M, they do not use proprioception during pre-training. They only add these inputs post hoc. And compared to concurrent work like OpenVLA or CrossFormer, they do not handle such high action heterogeneity. And of course, there are many similar designs, which is a good thing because if you see so many people in the community that are doing similar things, it probably means you're on the right direction. So to train this network, we create very heterogeneous pre-training mixtures. And these include 52 embodiments with 41 real robot teleoperation, 7 simulation datasets, 1 deploy robot datasets, and 3 human video datasets. Again, each of these robots has a different proprioception space. If we don't use this information, then we're basically throwing out half of the data. And each of the datasets is represented by one color here in the pie chart. We scale the model up to 1 billion parameter and train it for several weeks. So now let's get into one of the earliest investigation into scaling laws for robotics. So in this case, the x-axis is the number of samples seen, and the y-axis is the average validation loss. We see that by increasing the batch size or by training longer, the performance would improve, measured by the validation loss. And similarly, we can apply it to adding more and more embodiments. So in this case, the x-axis is the number of datasets or embodiment. So the hypothesis is that the trunk contains some information that maps from perception to action, which is shared across all embodiments. And importantly, now we just talk about pre-training. During transfer learning time, when we have a new embodiment, for instance, in the lab or in the simulation, the trunk transformer can be frozen, and only the head and the stem needs to be reinitialized, which often only has 2% of the parameters. And this is what we would use to pre-train and what we use to transfer. So this is the representation learning part. So in terms of the results, for transfer learning, we evaluated HPT trunk representation in 6 different simulation benchmarks that are not included in the pre-training process. In this figure, we showed improvement of the test success rates by using HPT pre-trained model rather than using non-pre-trained HPT or train from scratch version. And in this case, we compare with other state-of-the-art in the recent simpler benchmark and note that RT1 is extremely performant because it's kind of specifically tuned for this benchmark. And one thing to note is that our model is among the easiest to use generalist model, and the improvement is often clear even by just looking at the transfer learning loss. And further, we show that the pre-trained HPT can be transferred to 2 different embodiment setups in the real world with minimal fine-tuning. The trained policies are often robust to disturbance and nuisance. It can outperform models that are trained from scratch. It can outperform previous vision-based representation. And we also show that by scaling up, in this case, HPT XL compared to HPT base, we can improve the performance. And this is a full real-world demo with different tasks in HPT. We're doing pet care for one of my collaborators' dog called Momo. The first task is pouring the water and then scooping the food, and then is sweeping the food. And each of these tasks is trained with 50 to 150 demos. And in some follow-up project, we investigated in heterogeneous learning the tactile domain, as well as 3D domain for sim-to-real transfer and video models. So in HPT, we're thinking of heterogeneous pre-training, where we have a separation of the stem, trunk, and head, and we're loading data in a distributed fashion where we're kind of assigning each of the module based on the loaded data sets. But we're still updating the model in every iteration, and we have a shared pool of them. So what if we push this idea to the extreme, in which the case where we have unlabeled or heterogeneous data in silo, meaning it's not very easy to share data, then we will have a decentralized learning setting. So to give a little bit more details, in this case, we would train separate local models on different data sets without sharing any data. And these models can only communicate asynchronously at a much lower frequency. So to give a sense of how hard this is, so it's not like PyTorch distributed data loader where we're averaging iterations. I'm talking about thousands of iterations or epochs. We're only allowed to average models for so long. And why do we care about this in robotics? Well, there are many reasons that we do not or cannot share data, right? First one is that we like to have a centralized cloud to store this data is very expensive. Also, it's not very efficient to process this data or sharing this data. For some of the companies, they don't have the motivation to share the data with other folks. So this will create the problem of data silos and privacy. And one of the core problems is that it's also make heterogeneity very hard. So in this case, if we're training 2 client models, local models, and then we average them, we can see that without heterogeneity, the average model looks good. But if we apply heterogeneity, we see that the average model would drift. Because we're only communicating after a very long extended period of local updates. So in the second part, we're going to talk about aligning representations. So in this work, we're going to motivate the fleet data by using Amazon robots. So these robots, they operate 24/7 across the years. And here we're showing a graph of the package densities compared to the local sites. And the left and the right figure shows some visualization of the sites. The packages that we saw during Christmas is very different from the packages during normal times. Or the packages in West Coast is very different from East Coast. And there are many deep questions like, how should the data be shared across the fleet? Should we pull all the other robots' data? Is it better to generalize or specialize? How to use unlabeled data? And most importantly, we're going to study, can we do efficient training without sharing the raw data? And instead, we're going to share the weights. So this leads us to one of the most common algorithms in distributed learning, which is called fed average. So it has 2 steps. It has a hierarchy of global and local model. In the first step, it updates the local model for many iterations. In the second step, it sends the local models to the global model and do an aggregation. So this is called rounding fed average, and then it goes on. So we are going to look into different objectives that we can apply to step 1. The simple algorithm of fed average with supervised learning, we can call it decentralized supervised learning, or DECA-SL. And we ask the question, can we apply self-supervised learning to this setting? and we're gonna denote this with DEC SSL. And very importantly, this is going to unlock a lot of unlabeled data. But it's unclear to us in the first place, can we learn a representation through this procedure? By representation, I mean that we first learn, like, we learn the entire network and we chop off the last layer, we reinitialize it, and then apply it to downstream tasks. So we're going to study the behavior and properties of this DEC SSL. In particular, we are going to use contrastive learning. So in particular, SimClear. So what does it do, right? In this case, it would apply to, it would create two noisy copy or two transform version of X, and it try to maximize their agreement in the feature space. For instance, we can have a dog image and we apply two Gaussian noises to them and try to maximize their agreements. Why is this a good objective? Well, first, we know that the objective of contrastive learning doesn't know it's a dog image. It could have been a cat image. And secondly, the objective also doesn't know if the downstream task is going to be classification or detection. So it's kind of agnostic and general. So we'll first look at a simple experiment on the CIFAR10 datasets. In this case, CIFAR10 has 10 classes, and the goal is to classify. The x-axis denotes increasing heterogeneity, and the y-axis is the classification accuracy. So as we increase heterogeneity towards the right, we can see that in the worst case, we can have 5 datasets where each dataset only has 2 classes of the CIFAR10. And the lines here denotes the upper bound of centralized SL and centralized SSL, where we have to pull all the data together. We first see that for DEC SL, if we distribute the data in this way, the performance drops significantly as we increase the heterogeneity. And this is because the distribution shift is creating a lot of problems. Like we talked about earlier, if we take too many epochs before synchronization, the average model is going to drift. However, for SSL, we saw this surprising flat curve. Even if we increase the heterogeneity and even perform with the centralized baseline, where it requires a lot of storage. So the SimClear type of objective somehow is more robust to this kind of delay synchronizations. And we further scale up DEC SSL to ImageNet, MS Coco, and the Amazon datasets. So in this case, we're comparing DEC SSL to DEC SLREP and to centralized SSL and centralized SLREP. We show an improvement over the SL version and almost matching the centralized version. And we also apply it back to the Amazon case. We see in this case, the DEC SSL also learn a representation that's better than training from scratch. And the improvement is even stronger when we don't have so much data. Okay, so now we have this observation. When we have labels, we still want to do SSL. This is very counterintuitive. So we want to understand why. And the hypothesis is that SSL objective helps learn a uniform representation that's useful for efficient and robust decentralized learning. And we are going to analyze this in the linear setting. So let's consider a K-way classification problem, where the goal is to learn a representation useful to classify each point, in this case from RD to a label K. So each color in this case denotes a specific class. And we're going to do decentralized learning. So we'll create K datasets and we do local training. Once we finish the local training, we would average the representation. And we can see that one of the optimal solution can just be this standard unit basis. This would be very useful if you want to do the downstream classification, K-way classification, because if we just use this standard unit basis and we project the data points to it, then we will see that we just need to take a softmax, right? Or just read out the maximum coordinates. Then we can classify the class correctly. So I'm going to talk about what is DEC SL and what's DEC SSL different in terms of learning the representation. But we first describe how we are going to create this heterogeneity. So we would distribute most of the dataset class 1 to dataset 1 along axis 1. And we'll distribute most of the class 2 along axis 2 to dataset 2. And for DK similarly. So under this assumption, our claim is that the representation of local and global SSL is closer than SL. And note that in this case, the SSL would have the same color for all the dots because it cannot see the class labels. So if we learn the representation, we will show that SSL learns multiple direction to capture the intrinsic structure of the data. And once we average them, the learned representation is still pretty good. But for the SL case, it would be heavily biased by the labels. And if we average this, the learned representation might not be so good. And let's dive a little bit deeper into details. So in this case, SSL, we can write its objective and parameterization this way. So we parameterize F as W, which is our representation. And similar to SimClear, we're going to add Gaussian noises to X, compute the features, and maximize their agreements. And if you think about this objective, its optimal solution is actually the same as matrix factorization, or the PCA that you saw on the top right corner. So even if we have some sparse data along some sparse axis, in order to maximize the projection of these points on the weight space, it has to learn some axis along those rare directions. So the informal result is that the inner product of this representation with many axes will be high. Whereas for SL, we are going to do this setup where the parameterization is first learn the W, which is the representation, and then apply a linear head, which is V. And the objective is similar to the SVM there, where we're trying to maximize the margin of classifying the correct label Y versus the wrong label Y prime. And the informal result for this is that because it's doing this max margin, it really has to spend a lot of capacity in classifying this majority of data along this main axis well. So it has to mostly learn axis 1 in this case, and doesn't have so much motivation to learn other axes. So the learned representation would not be as uniform as the SSL case. So these two derivation combined justify our empirical observations. So now if we talk about pre-training project, we are going to move on to applying merging representation to merging policies. So for this project, for the sake of time, I'm going to just use two slides. So recall this is the standard Fed average where we're running local updates. And one problem that we talked about earlier is that if you run too many local updates, then the models become misaligned. So we're going to propose a new algorithm called Phillip merge, which basically add like a step 1.5 between these two steps. And the key idea is that before the global aggregation, we're going to align the model. So how are we going to do this? Basically, we associate a permutation matrix with each of the weight in the neural networks. And then we will update the permutation matrix in a iterative fashion. And once we are aligned, we will merge the model. Okay, so along the line of DEC SSL and Phillip merge, there are follow-up works that create function nodes that handles permutation symmetries, and also works that study the multitask aspect of linear fleet learning. So now we are going to take even one step further. We're saying that like in the decentralized learning setting, although we are training the model separately, we still have access to their weights, and we are still allowed to communicate every so often. But if we push this idea one step further, we will say, okay, all the models are now just fixed, and we can only have access to the outputs of this model. And we're going to see if we can kind of compose these skills to make it generalized at test time to out of distribution scenarios by this idea of composition. So let me first give a motivation for compositionality for out of distribution generalization. For instance, if we are collecting data for using a hammer to hit the pin, or using the wrench to twist the nuts, we probably want our policy to be able to use a wrench to hit a pin as well. We don't want to demonstrate every single combination of these tasks. And if you think more generally about tools, if they're embodiments, then we are saying that we hope to generalize to n squared by using just n of data. And this can be very significant intuitively because the n in robotics is quite big. So the goal of this work, called policy composition or POCO, is to build a general framework by using diffusion models. In one intuitive way to understand this is that the tasks that we talk about, each of them can represent an energy landscape. And then at inference time, we can compose their gradients as if we are composing the objectives. And then if you're optimizing this, hopefully we can get the best of both worlds. So specifically, what are the things that we can compose? We first look at the formulation for behavior level composition, where we are encoding analytic trajectory costs. Two very standard classic trajectory cost function is smoothness cost and collision avoidance. So because these costs are differentiable, we can compute their gradients at test time, and we can add it to the diffusion models. And for instance, we can have a policy that works really well, but you sometimes have collision. And potentially, if we add these gradients, it can help reduce the collision problem. And we can also apply POCO to compose different tasks. For instance, in this case, we're showing the two-use tasks, and we can do this through classifier-free guidance. So we will learn a condition network using the language instruction and learn an unconditioned network. And at test time, we can compose them flexibly to make the policy more hammer-like, for instance. And finally, when the robots are really trained with different modalities in different domains for the same task, we can just have separate models. In this case, we have a model that handles image and tactile inputs, another model that handles point clouds, and also the one is trained from simulation and the other one is trained from real world. And then we can just combine them to have the best of both worlds. So putting this all together, POCO allows addition of policy components at inference time to generalize out of distribution. And to generate the data to evaluate this in simulation, we use the state-of-the-art Drake simulator. We built a two-use benchmark by using a trajectory-based motion planners. And for the real-world data, we would just use joystick teleoperation. For the human data, we create a video tracking and segmentation pipeline that allows us to extract mask and point cloud from raw video data. So here we show that POCO are used to solve multiple two-use tasks. And what's really cool about this robot policy demo is that they're really trained with different domains and like policies or modalities or tasks and compose them at test time. And for instance, one example is that when we're doing the hammering task, the simulation policy can be very generalizable, but the motion is not as smooth. It can be quite jerky, but the real world policy can be smooth, but it also generalizes less as well. If we can compose them, potentially we can outperform either one of these domains. And in further collaboration work, we extend policy composition to long horizon tasks with human physical guidance, as well as leveraging haptic feedback in data collection. So as a summary, I discussed 4 works towards fleet learning as my contribution. We demonstrate how to scale up robot learning to go from homogeneous data, such as GPT, to HPT. We demonstrate how to learn from unlabeled data in a decentralized fashion to go from DEC-SL to DEC-SSL. And we also propose to align the model before we merging them. And finally, we see how we can generalize in a combinatoric fashion, given only factor of this data. And I hope I've convinced you guys that carefully designing methods to handle this heterogeneity is a very important and challenging topic, especially in the era of robotic foundation models. It also goes beyond robotics. Many fields that want to apply this apply machine learning but have the heterogeneity data problem can benefit from these methods. And now we're going to bring data back with fleet learning. Now we can deal with proprioception with heterogeneous pre-training. We can deal with fleet data with like SSL and fleet merge. And we can also reuse trend policy by using POCO. And hopefully with interpolation, we can get our generalizable policy back from heterogeneous data. And of course, this is only just a first step. There are many more future works required. There are 4 pieces of building a heterogeneous robot learning systems, and there are many underexplored and fundamental questions for each one of them. For instance, for data, what is the right mixture? How do we use data beyond RGB and teleop? For algorithm, how do we train in a task agnostic fashion beyond just supervised learning? How do we do that efficiently with petabytes of data? For model, how do we achieve a zero-shot generalization capabilities? How do we give the model a physical common sense? And for evaluation, how do we scalably and confidently evaluate a large amount of fleet of policies for complex tasks? Should we use simulation? How do we build high fidelity simulation? And zooming out a little bit, other than just robot learning and generalization capabilities that we discussed today, the robot needs to be very reliable, no matter if it's doing one very complex tasks or doing tasks in very complex environments. And we see if we want these autonomous robots to behave like the YouTube video here, it needs to have a certain amount of reliability. So the important debate in the field right now is scaling enough, or should we all study scaling for the physical world? I'm not sure if I have an answer here, because we all know robotics is very complicated with hardware, software, AI, and embedded systems. But what I've observed is that the compute and the hardware costs are going down. So I'm quite confident that in the future, the robots would have much better dexterity and planning skills. So in conclusion, we've seen foundation models to emerge in language domain, language to video domain, as well as multimodal domains. Today's large model, they can hear, they can see, they can read, they can draw, speak, and write. And I wonder when we can see a model that can sense like a human with all different kind of modalities and act in the physical world. And I think we are all looking forward to what's next for robotics. It's going to be a very exciting times.